Hello everyone, this is Anna Batkiewicz at Nikolaus Copernicus University in Toruń, Poland. I'm delighted to welcome you on behalf of the organizing committee to the third series of seminars sponsored by the European VLBI network, focusing on high-resolution radio astronomy. I want to mention just a few logistics of the webinar before we begin. You will be muted throughout the presentation, but you are invited to type in any questions you may have for our speaker through the Q&A facility. You can send in questions both during and after the presentation, but questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We will aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. Now, Emmanuel Bempong-Manful from University of Manchester will introduce today's speaker, Jack Radcliffe.
All right, thank you, Anna. So our speaker for the first talk for this third series of the EVN seminar will be Dr. Jack Radcliffe. Jack had his PhD, actually a joint PhD from the University of Manchester and the University of Groningen in Netherlands. And after that, Jack went on to take a research associate position funded by the UKRI at the University of Manchester for a couple of months, and then moved on to South Africa at the South African Radio Astronomy Observatory, where Jack held a postdoctoral fellowship position alongside a part-time lecturer position as well. And then moved on to the University of Pretoria, also in South Africa, as a full-time lecturer, where he is currently based, and also holds, alongside this position, an honorary research fellowship with the University of Manchester. Recently, our speaker, Jack Radcliffe, has been appointed to the EVN PC, and also currently chairs the SKA VLBI working group. I must say that Jack, with all his doings, is probably one of the very few persons, if not the only one, actually specialized in wide field VLBI. And so Jack is the go-to person if any of our participants are thinking of doing something interesting on wide field VLBI. So Jack, thank you for accepting our invitation, and I'll hand over to you now, Jack. Yeah.
Thanks, Emmanuel. Great. Can everyone see the screen? Okay. Perfect. Just move this so I can actually see my slide. Okay, great. Well, thanks so much, Emmanuel, for the introduction, and thank you everyone for joining here, and thanks of course to the organizers for giving me this opportunity to speak to you all today. It's a real honor to be able to open this third session of the EVN seminars, and I sincerely hope that I'll be able to live up to what Emmanuel has just said. And so today, basically, I'm going to start talking about how the work that we've done in our group here and in the previous around the world has enabled us to be able to see the entire radio, the entire sky now with using VLBI. So this is my outline for today. I'm going to give a short introduction to Very Long Baseline Interferometry. I'm going to talk about how we are surveying with VLBI. I'm going to talk about some of the science of this, and I'm going to talk about what's happening in the future. And in this case, you know, I'm going to be basically mostly be talking about centimeter VLBI. Now, there's the new area of low frequency VLBI, as seen by the International Low Far Telescope, and I'll touch on that a little bit later. So for those who here aren't VLBI astronomers or radio astronomers, VLBI is simply the fact that we've got telescopes distributed across the globe, and we combine those signals to basically replicate a telescope that is on continent scale. So this can cover frequencies from just 55 megahertz to 350 gigahertz, and these telescopes can be distributed in space in the South Pole. And the very, very long baselines, which for non-radio astronomers is the distance between two antennas, or the longest distance between two antennas, what can give you milli or micro arcsecond resolution when you combine them all together. So in this slide, you can see three of the most famous ones. I think I wouldn't be invited again if I didn't include the European VLBI network, which is on the top right here. We have the Event Horizon Telescope, who made those beautiful images of the supermassive black hole. And of course, we've got the Very Long Baseline Array, this homogeneous array in the United States, which has been operating for an extremely long time now. And VLBI science has been really, really impactful. And I'm just going to give you a disclaimer here. I am really sorry to everyone if your science area isn't included here, but it would be a lecture course, never mind a talk, to be able to cover everything. So this is just some of the highlights which has happened in the past few years, or over the past few years. And, you know, we've got things like localizing transients, such as the fast radio bursts. And it's the power of VLBI having the extremely, extremely high resolutions that, for example, we can locate these fast radio bursts to star-forming regions within extragalactic systems. You won't be able to do that with a standard connected interferometer because the resolution is high enough. We can also use VLBI to map the ejector of tidal disruption events, as this central bottom plot shows from Mattila et al. And we can look at spectral lines like masers, as Ross Burns did in 2023. And it shows the masers following the feeding, these spiral density waves towards the central protostar. And of course, the standard VLBI sort of science is looking at black holes. So here's a microquasar SS433. And looking through this over time, as you can see by the animation in the bottom right, you can see individual plasma blobs being ejected from the system. But VLBI isn't just about what's in the sky. Well, it is if you want to map the structure of the Milky Way, but we can also do things like spacecraft tracking and planetary atmosphere. So as it passes through, we can look through the signal delays, and we can turn VLBI on its head, and we can say, okay, well, if the sky is static, does the telescopes move? And because we have to know the telescopes to within millimeter precision, we can track how plates are moving over time to within a millimeter every year. And finally, because of the extremely high resolution, VLBI has also been pretty much the instrument to define what our coordinate system is, our International Celestial Reference Frame, which we all use every day, which is shown in the bottom right here. And finally, no talk would be complete without including the amazing results of the Event Horizon Telescope of M87 on the left here, with the polarization contour lines shown in the left. And of course, our own galaxy, Sagittarius A star, our own supermassive black hole. And we can see the shadows of these two beautiful objects, which has pretty much revolutionized the science of VLBI going forward. So when we look at this and, you know, we see all this amazing science results, these have all come from all of these many, many, many surveys that we see here. So what you've got plotted on this Moleweed projection of the sky is every single VLBI survey since that's in the archive of either the VLBA, the Very Long Baseline Array, the European VLBI network, or the Long Baseline Array in Australia. And what you can see here is that you can see the galactic plane where there's lots of observations, but at least from about -35, -37 in declination, VLBI covers quite a lot of the sky. So, you know, I should just end the talk here and say, well, we've already seen all the sky with VLBI, apart from the south. So the end. Any questions, anyone? But this isn't exactly the case. And the main reason for this is if we go and zoom into one of these pointings, so I'm picking this pointing here, see it's covered by 10 hours, and this is the famous cosmology field. So I've zoomed into one of these pointings, and in the background on the right-hand side, you can see the beautiful image from the Meerkat SK precursor telescope, showing a combination of hundreds and thousands of AGN, of active galactic nuclei, supermassive black holes ejecting jets with these giant radio galaxies, and a mixture of star-forming galaxies in there as well, at the fainter flux densities. So if say we wanted to observe these objects, all of these hundreds of objects with, say, the VLBA, the Very Long Baseline Array in America, then we could just take our telescope, go and have a look at this, and observe all of these sources similar to the image that we've got with Meerkat. And if we could do this, then why can't we simply just go back to these data sets and image the rest of the primary beam? You know, we've got these hundreds of thousands of data sets, but we don't have the hundreds and thousands of VLBI sources that we'd expect to see, as we can see with the Meerkat image in the background. So the issue with this is an effect in radio interferometry called smearing. And smearing is basically a breakdown of the interferometer equation. For those who don't do interferometry, it essentially messes up your images. And it distorts your images due to averaging of data in frequency and time. So we've got a zoom in on the right-hand side, showing the Meerkat's sources in the background, and the white circle is the VLBA primary beam, or the field of view, effectively, of your VLBI observation. Now, if we look at the center, which for VLBIs, this is the delay tracking center, this is where your correlator focuses all your signals, then when you go to high resolution, your source kind of looks okay. It looks kind of normal. So you can see here, this source in the center, this is only demonstration purposes, this is the real source, looks normal. So there's just got kind of a two-jetty thing, nice little AGN in the center. Now, as we move further away from the center of this primary beam, we end up getting this effect where I don't think anyone's ever seen a source that looks like this, or naturally looks like this. And we end up getting this smearing effect. And this smearing effect is proportional to the baseline length of your instrument. So you can see in the image here, Meerkat is not affected. It doesn't get stretched towards the center as it does in the VLBI observations here. And this is basically due to the averaging. So if we take the same averaging in time and frequency of our data, then the VLBA's effective field of view is just 40 arc seconds. So this is a much smaller than what it technically can see at once, which is about 25 arc minutes across. So you can see this in the right-hand side. The white is what we should expect to see, but because of the averaging, we can only look up to this amount of the sky. So as a result of this, we can't go back to the original observations because this is done in the correlator. So this is the thing that focuses, essentially it acts as the lens for your interferometer. And because you can't go back, because the baseband data, the voltages are extremely high data rates, so large storage, and you have to delete them, we can't undo this. And so as a result, historically, most VLBI surveys are targeted. So your principal investigator will see something normally with another telescope and say, hey, what's happening at high resolution in this single object? And the single object is the only thing you can see. You can only see this 40 arc second area or less in the center. So this sort of graph, this plot that I showed earlier is slightly misleading. Every single one of these points, you're only observing maybe half an arc minute, or you're only able to map half an arc minute of that field of view. So the amount of sky that VLBI actually looks at and can map is extremely small, even with all of these hundreds of observations. So part of the reason for this is not because of the instruments, limiting their scope. It's simply because you have to average in much, much finer time and frequency resolution. And that in turn makes your data size extremely, extremely large. So back in the 1990s, if you were wanting to image the entire primary beam of an array, you're looking at data rates or data sets that are terabytes in size. And I don't know, I was in nappies in the 90s, but I don't think any computer then, apart from the supercomputer, would be able to cope with a terabyte size data set there. So this is also why VLBI was typically confined to this small field of view in the center. So over the turn of the millennia, people started thinking, okay, well, the computers are getting better. Our capabilities are getting better. Our correlators are becoming more proficient. Why don't we have a go at this? So I'm going to use this as an example to show how this method, or the way to map the primary beams, were conceived using this example. So this is an example using M82. On the bottom center, you can see M82 as seen by the VLA. It's a beautiful star-forming galaxy. I've chosen it because it's just amazing. And you can see all these supernova remnants, and VLBI can be used to track these. So let's say, for example, you wanted to map the entire optical extent of M82 here. So the one way you could do this is, as I've just said, you can just deal with this problem by correlating or making your data with very, very fine frequency and time resolution. Now, the problem with this is that you end up with huge data rates, which all gets pumped into one data set. The data is also going to be 99.999% noise. So you're basically going to be looking as a needle in a haystack. And if you want to map the entire primary beam, you're looking at 10 to the 11 pixels. So you're looking at a 10 terabyte data set, which is very, very unwieldy. And this, of course, meant that you wouldn't be able to do this for every observation. So this method was the original way of doing this. And back in 2001, there was the first basically wide field deep survey. And what you can see here, this is the Goods North deep field, plus 60. And we have the background. This is KPNO. This is the optical. In the background, we got WSRT low resolution contours. And by Mike Garrett et al., they did this ultra-fine temporal and frequency resolution and mapped 3 sources in the same observation. This then, over the years, as computers got better, and the capabilities of the correlators got better, we went from seeing 1 source to seeing 6 or 7, Garrett et al. In the Bootes field. And then in the same Goods North field, as observed in 2004, the global VLBI observations of Chi et al. Saw 12 objects all at once using this technique. Now, the big problem with this is it's really, really inefficient. You can look for VLBI sources, but if you don't have a low resolution counterpart, you're not going to have a VLBI source either, unless it's transient, of course, which is very rare. So a new method was devised, which basically parallelized this entire process. And this was the shift in average method, or the multiple phase center correlation, which came from Adam Deller and John Morgan in 2011. And in this way, what happens is we do this fine temporal and frequency resolution, and then we move it around the primary beam. So we phase rotate is the radio astronomer word. And it works like this. So you take a little bit of a time chunk. This is your field of view, this blue circle here. And we correlate the data. This is our field of view. And then we move it around the primary beam to map the portion of the sky that we're interested in. And you can see already that this method is more efficient. We're not mapping parts of the sky which won't have VLBI sources in, or that we don't really care about. If there's just background sources, we don't care about that. But we care about the supernovae, which is sat in the middle. And then you keep on doing this over time and you build up your data sets. Now, the data size is still very large. You still are looking at big terabyte data sets, but these are split into individual data sets, which are small, and you only need to calibrate one of these. So it's very easy to be able to calibrate the data set and then cast all of these solutions or the calibration tables to all of the rest of the data sets. And because they're all independent of each other, it followed on from the way that computers were working at the time with multiple cores and distributed computing in recent time. And you can pick these for just being sources of interest, such as you could take a VLA survey, search for these, oops, oh no, I've got to go through this again. You can take a VLA survey, look and say, okay, there's all these sources and I'm going to target all of these sources directly. So this is how the method of wide field VLBI is done now, and this is a pretty revolutionary method of being able to map the entirety of the sky using VLBI. And using this, we have a distinct increase in the number of sources that we can target. This is true of the most recent observations, but there's also a bunch of other papers by Middleburg, Morgan, Rabindranath, Herrera-Ruiz, and Najiri and Roger Dean recently. And you can see that, we can target now thousands of sources in a single observation, or multiple observations. So on the left-hand side is an entire survey of the Cosmos field, where they targeted over 2,000 sources with about 400 detections. And on the right-hand side is the same Goods North field, which I targeted in my PhD with the same background here. And we're going from 3 sources in 2001 to 12 sources in 2004, and now to 31 sources in 2018 or 2014 when it was observed. So what about the science for this? Well, what does a statistical sample of VLBI detected sources allow us to do? So the first thing it can do is, of course, look at supermassive black holes. VLBI typically selects active supermassive black holes, and you resolve the radio core using VLBI. And galaxy and supermassive black holes are important. There's a coevolution. You can see in the plots here, at the bottom left, you've got the star formation rate history of the universe, peaking at about a redshift of 2. And on the right, we've got the black hole growth, which also peaks at a similar redshift back in time. And of course, if you look at the correlation between black hole growth and properties of the galaxy that it's hosted in, we can see that they must co-evolve together. The advantage as well with having radio is that we're not reliant on dust corrections. So radio can see through the dust, and you can get a nice, easy way of being able to measure both of them. And of course, by having coevolution, this means that you can also map feedback. This feedback is, of course, needed in simulations to replicate the high number of high-mass galaxies in the local universe. And we observe this in individual galaxies and groups and clusters, as we can see on the right-hand side here, which shows the blue, it's the X-ray. We can see the radio producing these X-ray cavities and the background optical observations. And we think that this can either promote star formation, say, preventing cold gas falling on the central galaxy, or it can promote star formation by either the mechanical energy of the jets or the winds can cause gas clouds to collapse and produce stars. Now, for us to be able to understand the coevolution of the supermassive black hole or the active galactic nucleus and star formation requires a complete synthesis of AGN activity. And this is where VLBI can also help. So typically in distant galaxies, any VLBI detection is a surefire sign of an active supermassive black hole. Most crucially, it's also independent of multi-wavelength data, and it's a unique sample. So you can see on here, we've got this VLA low-resolution image of this jetty black hole. From the VLA alone, you know this is a supermassive black hole with its jets north-south here. And then when we zoom in, of course, with VLBI in high resolution, we can see the core of the supermassive black hole where the jets are coming from. However, the majority of those sources that, remember, you saw back all the way in that meerkat image are point sources. And there is no way from just looking at the low resolution data, say in this case here on the VLA on the left-hand side, that this radio emission is from an AGN. And it is only by using VLBI and its high resolution, as we see on the right-hand side, that we can isolate the cores and see the black hole sat in the center. So we can use this as an independent way of finding AGN. And as an aside, it's also been shown now that low frequency VLBI used in the International Low-Far Telescope can do the same. So this is a piece of work by Fritz Zwein and Leah Morabito. And because you've got ultra wide fields of views due to low frequencies, you know, remember lambda over D is your field of view basically, where D is your baseline, lambda is your wavelength. You can look at basically degrees of the sky all at once, and you can map all of those all at once. And so by using the long baselines of LOFAR, you can still identify these AGN through these high brightness temperatures, i.e. this means that the radio emission can't just be from star formation. And this is a new area now, which is pretty much quite exciting for being able to do new AGN studies at high resolution. And they showed here, using the Lotman hole data, that 940 AGN were identified, and these were pretty much 4 out of 5 were confirmed through other multi-wavelength diagnostics of AGN. So we think this is reliable. On top of this, as well as just identifying AGN, the use of wide field VLBI to get statistical samples of active galactic nuclei can be used to find to investigate AGN physics. In the recent surveys on the left-hand side, there was this hint of this increased compactness towards lower fluxes. And this was suggested by Herrera-Ruiz in this plot here. This is VLBA divided by the VLA. So if this is the ratio of the fluxes of VLBI to low resolution. That's short. So stuff which is higher on the y-axis is more compact. And they hint that as we get to lower and lower flux densities, somehow in this plot, we start seeing more increased compact. We see more compact sources. And this could be either due to faster jets or it could be with Doppler suppression. On top of this, we can also look at, as I said before, AGN feedback or composite sources. This is an example from the recent VLBA survey of the Goods North field by Ant Najiri. And we see this merging system. It's kind of a redshift 1.2 analog of the antenna galaxy with about a star formation rate of 100 solar masses per year. And until this observation, we didn't think there was anything else happening apart from the star formation. And then we ended up looking with the VLBA and we find this black hole. So through looking at this, knowing the black hole is coincident with the stars being formed, we can start looking at more and more of these sources to gain a picture on what the feedback is happening in these objects. And of course, we can spread this. Some of our students here, Theo, who's just about to finish his master's and start a PhD, is looking at the AGN subjects in these objects, so using VLBI and slightly low resolution E-Merlin. And this is his first images that he made a few weeks ago. And he can do this to basically map how the source changes over the resolution and whether there's these little subjects present and whether these can influence these star formation rate estimates, which just use the low resolution flux. And on the right-hand side, the master student, Paul Wilsonach, has been doing this observations of a source which shows helical structures as only seen by VLBI and the VLBA, and whether this is due to possibly a second supermassive black hole present in this object. Furthermore, on top of this, the fact that we've got a sample of VLBI observation sources, we find serendipitous discoveries, of course. This is a parameter space that no one really has looked at because, again, as I said before, we're looking at very small portions of the sky. And just through the two surveys, the Cosmos survey and the Goods North survey from 2018, we found binary supermassive black hole candidates. So there was two in the Cosmos field by Herrera-Ruiz in 2017. And on the right-hand side, work by Anneke van der Dusen, who's my master's student, has found this possible dual supermassive black hole at a redshift of 1.6. On the middle top here, you can see the two VLBI detections overlaid on top of the HST near infrared, which kind of has two peaks around this side as its morphology. And then when we looked at the HST GRISM for the O3 lines, we have two peaks corresponding to these two positions. And she's just working on how reliable this is for being a binary supermassive black hole candidate at the moment. Just bear with me one second. On top of this, we also look at things like, we find things like supernovae. So this was back in 2019, and Zane Lentz did some modeling on this. So what you can see here on the left-hand side is the VLA. This is in 1996. This was in 2011, and this was in 2018. And we found this in the VLBI survey in the bottom right as a source. And then we looked back at the data and saw, oh, wow, there's a kind of a point source has appeared within the VLA data. As you can see here on the bottom left, where we've got E-Merlin showing the compact source embedded in this kind of diffuse emission from a side-on galaxy, as seen the HST near infrared. And this is at redshift 0.07, and its luminosity is consistent with low luminosity AGN or supernova. And then Zane, for his honors project, who's now doing a master's in lensing, tried to do some modeling of this, and we need to add some more data points to this in the future with other observations we have. But this all came from simply finding the VLBI source in this object, because the supernova is not visible in the optical. On top of this, we can also use wide-field VLBI to look at gravitational lenses. These sources are extremely rare. There's a beautiful example on the right here from Cristiana Spingola, showing the gravitational lens of a background AGN lens by a foreground galaxy, and the precise, or the extremely high resolution that VLBI provides allows you to look for dark matter substructures and allows you to constrain and furthermore, that means you can constrain the lens models. Now, for us to be able to, work out, okay, what's the profile of dark matter? Is there clumps? Is it warm? Is it fuzzy? We can use wide field VLBI to find more of these lenses. So at the bottom, Christiana looked at the M-Tribe survey, which is the wide field VLBI survey of the first sources, or the VLA first sources, and found 2 other candidates, which could be gravitational lenses. On top of this, you can also use VLBI, as I said before, to look at these nearby galaxies as well. This is why I chose M82, because it's beautiful. You can see the VLA inset on top of the optical on the left here, Josh Marvel, and the Chandra in the green and yellow, and the HST in the green and yellow, showing the outflows coming from this kind of supernova / star factory at the center. And we can use VLA and E-Merlin to peer into this. This is at the top. This is from Tom Huxley, showing the H2 compact H2 regions and all of these supernova remnants here. And then we can zoom in even further into these objects using VLBI to trace the ejecta of these objects. And the technique of wide field VLBI can be used to just map this entire region and allow us to see these serendipitous objects, which may not even be in this plane, as we can see here. And it also allows us to map things already known. So here's a supernova remnant from 1986 and 1997, and then the recent observation in 2022. And my student, Sibo, is working on some of this data at the moment. And finally, VLBI surveys won't be useful without having technical progress. And over the years, there's been a few techniques which have been developed, which allows us to basically reach any portion of the sky using a VLBI instrument. So one of these is like multi-source self-calibration, but we also have now end-to-end VLBI pipelines. So for those who may have gone to sleep by now, if you want to do VLBI, you can shove it through a pipeline and get an almost calibrated data set out the other side. So 2 of them, which are present at the moment, is ARPA-CARD by Michael Janssen, and VPipe, which I developed, which allows you to basically calibrate VLBI data without having to know the bells and whistles of VLBI observations. And finally, I just want to say one of my students, Llewellyn Codser, here is also developing primary beam models for these arrays, as you can see on the bottom right. So moving forward from this, what's next for being able to survey with VLBI? Well, there's big instruments coming. Meerkat is here in South Africa. I don't think I'll be allowed back in the country if I didn't talk about Meerkat. And on the right-hand side, you can see the first fringes using Meerkat. And this will be an excellent instrument for us to improve our sensitivity and for us to be able to punch through that microjansky regime of observations. We, of course, have the square kilometer array. If this is combined into a VLBI array, we will have an order of magnitude more sensitivity. And it's worth noting as well that if we get long baselines, as is hopefully may happen at the LBA sites in Australia, we would have an international LOFAR telescope in the south as well, which would cover both hemispheres of the sky. And the key thing about this as well is that even with the SKA coming online, you can't ignore VLBI. So what in this plot here, you can see the angular resolution at 1.5 gigahertz. On the top, you can see the physical scale at redshift of 1. And you can see the various UV coverages or the UV ranges. So this is the spatial scales that they're sensitive to, or the resolutions they can detect. And you can see that VLBI still will occupy, even with SK1 mid, a unique space to be able to probe the extremely high resolution sky. So you're still going to need to have VLBI observations to be able to observe all of these objects in the future that the SK may pick up. And finally, of course, we have the NGVLA. And this is basically going to be kind of a VLBI instrument in itself with a compact core, giving you milli-arc-second resolution and insane imaging capabilities, along with these long baselines at the current VLBA sites. So this would be truly revolutionary, still far, far away. This is extremely far away still. Finally, so this is kind of in the future, but what can we do now? What can we do to be able to observe large portions of the sky right now? One of the things that we've looked at is commensal surveys. So as I said before, your typical VLBI observation only cares about the thing in the middle. You can only observe the thing in the middle because of this smearing effect, as you can see on the bottom left. To reduce the data sizes, the data is average, so it limits the field of view. But this means that all your VLBI observations throw away 99.9% of the data. And our aim here in Pretoria is to be able to do wide field processing on every single observation. So instead of just targeting the sources we see on the right, we want to target all of these sources as well. So you can use pre-existing surveys, catalogs, and we've got 3 pilot programs ongoing. We've got sweeps and the precise with the EVN and the EMU VLBI program on the LBA. And I just wanted to, oops, you might see things like this, hidden sources. I just wanted to finish with showing the first sweeps, first detection from this survey. This is by Celestine Herb-George from Groningen. And just to finish off, on track now. We are building a correlator here to be able to do this. So the goal is for us is that every single VLBI observation will be correlated in the wide field mode using a distributed correlator, so across clusters, correlating parts of the data. And the idea is that we basically will store and make all of these calibrated data and images available publicly so that people, say you have a JWST observation, you say, okay, is there an AGN hidden in this data? You can look through our calibrated data and images to see whether there's a VLBI source there. And this is the first light. So we've only been doing this for about 6 months old. This is the first supermassive black hole that I saw, using correlating using our own correlator here. And if we have full operation, you know, we're expecting to look at over 15,000 objects per year. So we expect that kind of in 2 years of data correlated in this way, we may be able to see more sources than have ever been observed with VLBI across the last 50 years. So these are my conclusions. Our high resolution radio studies are going to continue to play a vital and expensive role. We can do this for lots and lots of different science areas in astrophysics. And these wide field VLBI observations are at least possible with all centimeter wavelength long baseline instruments. And for those here who don't do VLBI, we've got pipelines. So non-radio users can use VLBI. Plus there's lots of training, accessible training and tutorials in VLBI, and there's extra support available. I think Benito is going to announce this a little bit later in regards to the EVN. And if we're able to do this kind of correlation of all observations, so we're not throwing away 99% of the sources, we will hopefully see a step change in the impact of VLBI. So we're going to have tens of thousands of sources, which would be an amazing legacy product in the era of these kind of all-sky deep surveys that are going to be coming online in the next few years. So thank you very much, everyone. I hope I'm on time and I didn't put you all to sleep.
Yes, excellent. Thank you very, very much. You are very nice on time. Thank you for the summary, for showing the nice results, and also for the perspective that we know where we are going and a lot of discoveries in front of us. So there is a question that since you mentioned the Meerkat VLBI, will that have multiple tight array beams?
It's unsure yet. I can't speak on behalf of Soraya on this, so we're not sure. That's the honest thing. I don't know if anyone from Soraya can comment on that.
Okay, maybe in the chat. What is the luminosity of that supernova remnants comparable to known objects?
Supernova remnant
I missed this
find-
slide, which was the maybe 24.
5 times 10 to the 22, so it's slightly higher than most supernova. We'd always expect to detect something on the slightly higher side, so that's why we're on the edge of whether it's an offset low luminosity AGN, because it's about 0.1 arcseconds from the optical center of that galaxy. So yeah, we're still unsure on what it actually is. We've got lots of kind of data to fill in that radio light curve from 2011 to 2016, and hopefully that will give us more inclination on whether it's consistent with a model of radio emission supernova.
Okay, thank you. At what frequencies does the VLBI operate? The one question is also.
What frequencies?
At what frequencies does the VLBI operate?
I think it's for anything from 55 gigs to 350 or more at the moment. Most of it.
Okay, so maybe we can also put some technical description, the link to this technical description maybe for the audience. Okay, and thank you. It was a great talk. Really enjoyed it. What strikes me when looking at the LOFAR multi-phase center VLBI images is that a lot of these sources have significant structure and aren't just a point source like the centimeter VLBI images you showed. This is partly because LOFAR only has 200 milliarcsecond resolution, but also because of the good UV coverage on a variety of scales. Does this argue that we should be trying to do wide field centimeter VLBI with EVN plus eMerlin plus VLA like baselines at once? I know it is already challenging to do wide field VLBI with just 10 milliarcsecond resolution, but it seems like having an access to from 1 milliarcsecond to 10 arcseconds case would be really epic.
I totally agree, Jason. This is why I think the NGVLA is going to be a big, going to have a big impact on this, because that will essentially do that. At the moment, of course, the EVN has eMerlin as part of it, and that really helps with kind of giving you the arcsecond to milliarcsecond resolutions. But there is some, I'm not going to go into it here, there is lots of subtleties in the way that you correlate the data, for being able to get kind of thermal noise images. It's something that we've started to try and look at. So the best thing you can do at the moment is essentially observe with the EVN plus eMerlin and then try and add the VLA as it stands. It'd be really epic, but of course, when you start combining arrays together, you get a bunch of systematics, which isn't the easiest thing to solve. Especially with, yeah, we've tried this in Goods North using VLA and eMerlin and EVN together, but there is lots of issues manpower issues where we haven't managed to get it right just yet, I don't think. But it would be epic. Yeah, I would definitely agree. It's something we're trying. Let's
wait for this epic word. So you mentioned computational challenges for VLBI surveys during correlation in the 90s. What are the likely challenges for VLBI survey past 2030s, i.e. the SKA era, during to the sheer volume of data expected?
Yeah, I think the biggest challenge at the moment for it is just the operational models of these instruments. They're dealing with huge petabytes of data every second. And their current VLBI modes, unfortunately, give us a tide array. So we have a really restricted field of view. So if you want to go back to looking at the whole sky, something has got to change. So it might be actually the way that, whether they can incorporate external VLBI stations directly into the correlator. It might not be useful for SKA because they're fairly short baselines, but for the NGVLA, they're going to have the precision in the correlator to be able to do extremely long baselines anyway. So that might be a method to keep the field of view at the same time. But yeah, it's for at the moment, we think it's operational models and the way that you are going to correlate the data with regards to this smearing effect, because just as a subtlety, the smearing is, if anyone's going to sigh, it's a baseline dependent error in your data. And you can't get rid of those very easily, which is why you have to change the way you correlate.
Okay, thank you. And another and the Q&A. Other than AGN, what are science areas will low frequency below 400 megahertz, VLBI make an impact?
Sorry, I didn't catch that one. Is it in the Q&A? Okay.
In the queue, maybe. Yeah, I will also put in a chat for your convenience.
I'm not, to be fair, Tyler, I'm not 100% sure because I'm not a low frequency here. I've done a little bit on this, but yeah, most of it will be kind of radio halos and galaxy clusters possibly, and if there's any turbulence in these, but I'm not 100% sure. I'm just making up stuff at the moment. So so yeah, Leia Morabito is the super expert at this, so she'd be better to answer it than me.
Okay, we have maybe some answer from Javier Moldon that pulsars are bright at a low frequency, so maybe. So, and another question, the Q&A, does the current survey cover polarization? Would it be a bigger challenge for future surveys if including polarization calibration?
Yeah, it's extremely difficult to do polarization at the moment. VLBA is probably possible, but the big thing is off-axis effects from the primary beams, and how the polarization effects are done. Because lots of VLBI surveys have typically looked at the center of the primary beam, then the primary beams haven't really been mapped holographically. Trust me, I've been. It would be an extra challenge. If we had the primary beam models, I think it would be easy enough to implement that.
Okay, thank you. And now we have in this chat, not in Q&A, but in chat, what are the chances that VLBI detection at Z at the redshift Z or above 0.1 is certainly an AGN and not supernova remnants or some other emission processes?
Yeah, so this comes from an old paper looking at brightness temperatures of objects, and it essentially says that if you put a bunch of supernova and you take them from the local universe and you put them back at a redshift of 1, then it corresponds to a certain brightness temperature. So this is a Condon 1992, Lisa Cooley did this in 2000. And so at least up to microjansky sensitivities, we believe that pretty much 99.9% of everything that you detect above redshift 0.1 is an AGN, because no star formation can be that intense and that compact as well in the object in the galaxy to be able to produce that brightness of emission. So that's the main reason for that. But when we go down to so say if we include shorter baselines into our arrays like E-Merlin, then the equation changes a little bit, and it's something that we need to start thinking about as well. And especially, you either get shorter baselines and increase surface brightness sensitivity, or you go deeper, and then we need to start rethinking whether this is an accurate detection method for AGN.
Okay, thank you. Great description on the interest of expanding the field, which is imaged in the VLBI observation. In the coming future, we will have optical telescopes with comparable resolution, ELT, for example. Would you think that having these large fields imaged in both optical and radio at similar resolution would boost the science, or you would anticipate some challenges to combine both due to the different techniques, reference range, etc.?
No, if anything, they're going to be complementary to each other. It's partially one of the reasons why we're looking at doing this kind of commensal surveys, because you're going to have these all-sky surveys like LSST. You'll have some fields which are looked at by ELT, etc. And VLBI, of course, is going to be tied to the international reference frame. So in principle, you could map your optical observations to match the reference frames together. The extremely high resolution, of course, causes a problem because as you say, the emission mechanism is going to be different, so you can't exactly align them perfectly. So there will be some challenges, but having the optical is invaluable to all of this. You can't understand what's happening in the object until you see the multi-wavelength diagnostics and the images of these objects. So if anything, they're going to be complementary, but yeah, how we combine them together is a good point, and I'm not entirely sure, to be honest.
Okay, let's wait. Thank you, Jack, very, very much for this nice, the great seminar. I have learned a lot.
Incredible.
So we have another question in the Q&A dealing about the training course on the VLBI data. So we will answer in our announcement. So let me invite you for the next EVN seminar symposium, the seminar, EVN seminar on 26 March. It will be given by Benjamin Winkler about the dark sky. So it's quite interesting for radio astronomers, but I think for the whole community. And now Benito will also share some announcements. Thank you very much.
Thank you, Anna. Thank you everyone for joining. As Anna mentioned, we will have the next seminar on the 26th of March on Benjamin Winkle that works for CRAF. So all the initiatives that are to protect the radio bands, at least for astronomy. So everything that Jack has mentioned will be able to observe in the coming future. And we will also like to announce that we'll have the EVN Symposium and users meeting this year again, that it's a biannual meeting and will happen from the 2nd to the 6th of September of 2024 in Bonn, Germany. And you may have already received the first announcements, but in March, the registration and all the extra submissions will be opened. So I hope that many of you will join the symposium. And concerning one of the questions, actually, likely on the 26th of April, still we confirm soon, we will have again a EVN users training. So the idea is that during one day, all the super scientists of the EVN will show everything that you need to know to get observations with the EVN. So from how to prepare proposals, the parts that you need to do for the scheduling, although now we have a lot of programs where you don't need to be any expert at all, so anyone can conduct EVN observations. And this will happen in April, roughly 1 month before the next call for proposals. So it will give you time to get the idea that you need and then prepare a proposal for the observatory. So you should receive some announcements within the coming weeks, probably for that. And that's it from my side.
Yeah, so just to add to Benito's response to that last question. So there's also the CASA VLBI Data School, which also teaches PhD students or early career researchers or anyone who wants to get their hands dirty with VLBI data calibration and imaging. Yeah, this also happens every other year. So 2 years. This year it's not happening because the last one happened last year. So the next one will likely be next year, but announcements will be coming forth in due course. Yeah.
Okay, thank you very much for
Can I quickly
everyone.
announce something about the VLBI training as well?
Okay.
Sorry. Just for people who are either in Africa or want to come down to Africa, there is a possibility that we will have a African VLBI school sometime later this year. So keep an eye out for the announcement for that too. And there's an ERIS too. There's an ERIS in Granada. So keep an eye out for that.
Okay, thank you very much. See you in March.